So in today's video, we're going to look at 5.3, which looks at evaluating the fit of a linear model. We're going to look more in depth at that line of best fit equation and seeing how the errors are affected by using a line of best fit instead of using some other measure in order to summarize the data. Okay, so we're going to be comparing using our line of best fit as a predictor instead of using something like the mean as a predictor. Okay, I'm going to warn you now, there is a lot of algebra involved in this particular section. It's not the most intuitive chapter that we go through, but hopefully by going through this a couple of times you can see kind of what's happening, and it's looking at all the different types of error that we have. Okay, so just as a heads up before we start this, we know from chapter 5.2 that our line of best fit never hits all of the data points. Okay, so our model being the line of best fit, that's how we are modeling our data. We are predicting our data using that line of best fit. That model isn't going to be precise. Okay, there's always going to be an error between most of our data points and our line of best fit, because all of our data points don't lie on the line of best fit. You may get one or two that lie on there, but most of them have a pretty significant error between what the observed Y value was and the predicted Y value was when you use the line of best fit as your prediction. Okay, so we looked at that last time, and that happens for every single X value. We have that difference in the Y values. So our prediction is always going to have an error. Okay, we're never going to be completely on the money for every data point. So let's say that we incorporate the error into our particular equation. So our equation for our observed Y value is always our predicted Y value for that particular X value plus some error. Okay, because let's go ahead and draw this out. We did this last time. Again, I'm just going to go with some data that has a mostly positive correlation, and I'm going to draw my line of best fit, something like that. Okay, goes through the middle of my data. Okay, let's take this data point here. Okay, we can see that for that particular X value, so X value of that data point is down there. I haven't drawn my Y-axis long enough. Let me draw that slightly longer. Okay, we can see for that particular data point at that X value, okay, its associated Y value was around here. But using our prediction, our line of best fit, we predicted that the Y value for that particular X value was actually around there. Okay, so using our line of best fit as our prediction, okay, we have this error between our prediction and our actual Y value. And this is our error, the difference between our predicted Y value from using the line of best fit and plugging X into the equation of the line of best fit. And then we've got plus some error term here to equal the Y value that we actually observed. Okay, so we can always say that our observed Y value is equal to our line of best fit equation with that X value plugged in, which will bring us up to here. That's our predicted Y value using the line of best fit, plus the error term, whatever that error may be, and it changes for every single data point, and that error can be positive or negative. If you have a point below the line of best fit, you're going to have a negative error. Okay, so we have a positive or negative error. We add that on, and then we get our observed Y value for each X value. Okay, so we're going to incorporate this into our model so that we now have this equation here. So it's our equation of the line of best fit for a particular X value plus the error. Okay. We've looked at these errors last time, okay, and we said some are positive, some are negative, depending on whether that particular data point lies above or below that line of best fit, okay? And we said that because it can be positive or negative, in order to find the line of best fit, so the line that best fits our data, the line that most accurately goes through the middle of these data points, in order to find that, we try to minimize the sum of the squares of the errors. Okay, we square each of those errors to make it positive. Okay, to make sure that every single one of them is positive, because you square a negative number, you're going to get a positive. That means that we don't have to worry about them cancelling one another out when we sum them together. And then if we try and minimize that sum of the squared errors, then we can say, okay, we have the best line of best fit that I can find. Okay, so we always try to minimize the sum of the squares of the errors. So we did that last time. But when we do that, okay, if you have errors that are seriously large, using our line of best fit as a predictor isn't exactly very accurate. Okay, if you have some data points that are like way up off, like over here or down here, okay, using the line of best fit to predict what happens at that data point, let's say this one here, using the line of best fit as a predictor for that isn't exactly accurate. Okay, so if the errors are too large, it doesn't make sense to use our line of best fit as a predictor. Okay, because normally we can say, okay, well, I can predict what my y value is at any particular x value by just taking the y value that I get off of the line of best fit. Yes, there is some error, but it's normally fairly small in comparison. Okay, so we normally use that value that we get off of the line of best fit as our predictor for each x value. But if you've got some really, really large errors, okay, where you've got some data points that are way off of the line of best fit, using the line of best fit as the predictor doesn't make any sense. So we actually are going to go back and look at these errors. Okay. Whenever you have a line of best fit, the mean error should always be 0. Okay, let's think about that. What am I doing when I'm taking the mean? Okay, I'm adding together all of my errors and dividing by the number of data points, or the number of errors being the data points that I have. If I just add together all of my errors and I have got a line of best fit, what you should find is that all of these errors are going to cancel one another out. I've got some positive above the line, I've got some negative that are below the line. When you add them all together, if you have a line of best fit that is accurate going through the middle of the data, you should find that the mean error is 0. Okay, because the ones that are above the line give you a positive error, the ones below the line give you a negative error. You add all of those together, you should get 0. And then 0 divided by however many errors you have, however many data points you have, 0 divided by anything is still 0. So whenever you have a line of best fit, the mean of the errors should equal 0. So the mean isn't a great way of trying to figure out what's going on with the errors here to see if you have a decent line of best fit, because all those errors will always cancel one another out. So instead, what we are going to look at is how much the errors actually vary. Okay, because taking the mean of these errors doesn't help us very much, because it's always going to come out to 0. It's not a very good measurement, okay, when you just get 0 every time. So let's go ahead and draw this graph. So I've done this before, but I want a slightly larger graph to prove this and to show you how this is working. So again, I'm going to take some data points that have a pretty obvious positive correlation here, okay? And I'm going to draw a line of best fit, okay? Again, this isn't going to be accurate, but hopefully you get the point. Let's say it went through there. Again, it's not very accurate, but when we look at this, okay, I want to look at the variation of my errors. Okay, that's what this comes down to. If we look at this line of best fit, okay, and I look at the errors, the difference between each of the data points and their y value, so that's my observed y value, and the predicted y value from using my line of best fit. So let's look at the differences between those two. So for most of these, let's say I took this data point here, okay, my error is the distance between here and here, okay, that's my error. Then for another data point, let's say I took this one here and I look at the error here, okay. There's not a huge difference in those errors. Yes, one is positive and one is negative, but in actual size, there isn't a huge difference in my errors, okay. Now let's say I decided, okay, I don't really like that as my line of best fit. I think I can do better. Okay, this is just proving a point here when I do this. And let's say instead, I took this line and I said, well, this is my line of best fit. We can see obviously it's not. But let's say, no, I think I can do better. Here's another line of best fit. How can I tell that this is not my line of best fit other than it doesn't go through the data? Well, remember, I'm looking at my variation of errors, okay? So we can see here that the difference in the error for that data point has a huge difference compared to the error for this data point, okay? So we can see that for this second line of best fit, we have a huge variation in our errors, okay? So sometimes you're not actually necessarily looking at the size of the errors, it's how much they vary, okay? If you have a smaller variation in your errors, like we do with our blue line of best fit, you can tell that this line probably goes through the middle of the data. Yes, some are positive and some are negative, but in size, most of your errors are roughly the same size, okay? But if I were to take any other line and say, well, this could be my line of best fit, you would end up with a much bigger variation in your errors, okay? You could have one error that is only a difference of 2, and you could have one error that was 20, okay? You could have a much bigger variation in your errors because the line does not properly fit the data. So if you have a large variation, it means that the model, the line of best fit that you have, isn't very reliable, okay? So the less variation that you have in your errors, the closer together that your errors are, not necessarily the smaller that they are, but the less variation that you have in your errors, the more reliable your line of best fit is. And hopefully you can see that from this diagram, okay? Now I've been talking about the variation of errors. Whenever I say variation, what word does that remind you of that we've looked at in statistics so far? Well, it should remind you of the variance, okay? So when we actually look at a line of best fit, instead of looking at the mean of the errors as a good indicator of what's going on, because remember we said our mean was 0, so it doesn't really help us. Mean of our error of the errors is just 0. So instead what I'm going to look at is the variance of my errors. And that variance, the size of the variance of the errors, is going to tell us whether we have a reliable line of best fit or not. The smaller the variance means that the less your errors actually vary in size, which means that you have a better line of best fit. The larger the variance you have for your errors means that the less reliable this line of best fit is because it's way off of a lot of your data points and doesn't actually go through the middle of your data. So we are going to look at the variance of the errors. Okay. This has a very weird formula. You don't necessarily need to remember this, just kind of go along with it. I will tell you what it means. Some of this you won't yet understand until towards the end of the course. But the variance of the errors we actually denote by S subscript E squared. Remember when we did the sample variance and the sample standard deviation? Okay, the variance is just the standard deviation squared, which means that the standard deviation is the square root of the variance. And when we are looking at samples, we always denoted the sample standard deviation by S and the sample variation by S squared. Okay, the sample variance by S squared. So now, because I'm looking at the variance of the errors, okay, I'm going to denote that by SE squared. Okay. And the formula for this is this formula here, and I'm going to explain what some of this means. So you are summing over all of the errors. So you're summing over all of your data points here. Okay. This E with the bar across it, remember when we had X with a bar across it? That told us that it was the mean of all of the X values, the mean of all of the data points. So this thing here, this E bar, is the mean of the errors. Okay. Remember when we took the variance before, we did the data point minus the mean of the data point. We squared those for every single data point X, where we did X minus the mean. We squared that for every single X that we had. And then we summed all of those square values together. And then we divided by n minus 1 when we were dealing with a sample. Okay. This time we are dividing by n minus 2. And that is actually because we have one less degree of freedom due to looking at errors. Now, that's where I said that you may not understand that yet. That will come up more towards the end of the course where we look at degrees of freedom. Okay. It basically means you have more restrictions set on you. Okay, because you are looking at the errors and not the data points. But don't worry about that right now. We will come back to that at the end of the course, and that will make more sense. But for right now, all you need to know is when you look at the variance of the errors, you are dividing by n minus 2 because you have more restrictions on you as you are looking at the errors of the data points and not the actual data points themselves. Okay, so we are dividing by n minus 2. So this looks very much like the variance that we had for standard data points. Okay, we are now just looking at the errors. And so we're saying that we're taking each of the errors minus the mean of the errors. Okay, exactly like where we did the data points minus the mean of the data points. I'm squaring that value for every single one of my errors that go with each of the data points. Then I'm adding all of those differences between the error and the mean squared. I'm adding all of those together for every single one of my errors, and then I'm dividing by the number of data points I have minus 2. Let's look at this numerator here where I've got the error minus the mean of the errors. Now, what did we say the mean of the errors was? Well, we know that because we've got some points above the line of best fit and some points below the line of best fit, the mean of the errors should be 0, okay, because they cancel one another out. So the mean of the errors should be 0. So this thing actually simplifies. If I'm doing an error minus 0 for every single one of my errors, I'm just going to get the error. So this thing will actually reduce to the sum of actually the square of each of the errors divided by n minus 2. So all I am doing is I'm taking each of my errors for every data point. I'm taking each of the errors. I'm squaring that. So I'm squaring the error. So coming back here, I would square this distance here. Okay. I would square that, and I would do that for every single one of my errors. So I would square this distance. I would square this distance. I'm basically coming up with a bunch of positive numbers. And then I am adding them together. I'm summing them. So I'm adding those errors together, the squared errors together, and then dividing by n minus 2. Now, we have looked at this last time. the sum of E squared. Okay? I'm squaring each of the errors and then adding them together. Remember, when we deal with the line of best fit, I wanted to minimize the sum of the squares of the errors. That's exactly what I am doing on the top here. I am summing the squares of the errors. So all that numerator is the sum of the squares of the errors. I'm going to denote that by SSE. Okay? The sum of the squared errors divided by m-2. Okay? So all this is, okay, I'll write this out in words. It's the sum of the squares, or the sum of the squared errors. Okay, so I'm taking each of the errors, I'm squaring it, and then I'm adding together those squares. Okay, and I'm going to denote that by SSE for now. If I wanted the standard deviation of the errors, remember we like the standard deviation of data points because it was in the same unit as the original set of data, whereas the variance would have the square of the unit. So if I wanted the standard deviation of the errors so that I was back in the same unit as the errors, okay, all I would do, remember the standard deviation is the square root of the variance, so all I would have to do is square root this value here. So standard deviation of the errors is just denoted by SE, okay, because it's the square root of this thing. So SE is the square root of the sum of the squares of the errors divided by m-2. Okay, and I square root that. You're going to be doing some of this stuff on Excel. Okay, I'm going to assign this in the next couple of days. When you do this on Excel, you can actually come up with these values, and you are going to do that for your own set of data. When you are looking at the standard deviation of the errors, just as a heads up, on Excel when we do this, this value is called the standard error. Okay, so when you go ahead and try and find the standard deviation of your errors in Excel, its name in Excel is standard error, okay? When you are trying to find the variance of the errors in Excel, so when you have your data set and I ask you to find the variance of the errors, it's actually done under something called residual MS. Okay, so that's a side note for when we go ahead and do this in Excel. You'll have a data set and you'll have to find a line of best fit, but I will ask you some stuff about the errors, so the difference between each of the observed data points and the predicted value off of the line of best fit. And I will ask you to find out some stuff about the errors to see how much of a variation you have in your errors. And they are done under standard error for the standard deviation of the errors and residual MS for the variance of the errors. So, as I said, we want the variance of the errors and hence the standard deviation being the square root of that. We want these two values for the errors to be as small as possible for the given data set. Now, that is important. It has to be small enough given the data set that you have. Now, small can mean different things depending on your data set, okay? If you're looking at the diameter of a heart valve, for example, that is tiny, 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 okay? So if you were looking at many heart valves, and then we wanted to fit a line of best fit to the diameters of these heart valves for different patients, okay? Looking at the errors between the predicted value of the diameter and the actual value of the diameter for each of these heart valves is going to be absolutely minuscule, okay? So looking at the variance of the errors for that particular data set, because you are looking at something that has such a small measurement, okay, the definition of small there is going to be absolutely minute. But if we were looking at, let's say, Wall Street stock prices that are really, really large, okay, the variance of the errors in those data points, small is going to have a much different definition there, okay? So something that is small for one data set may not be small for another data set. Just as a heads up for that. So make sure when we say small, it's small in comparison to the data that you are actually looking at, because small is going to have a different definition depending on the data set. Okay. Now, I'm going to introduce some new terms here, and this is where it gets incredibly algebraic. Okay. We are going to look at how much of the error is actually corrected by using a line of best fit instead of using some other line. Okay, I want to see how much of the error can be corrected and how much of the error we are still left with. What do I mean by that? Well, let's say, again, I'm going to draw this out so that we can do this a couple of times. Okay, I'm going to have my data set here. Okay. Now, for each x value, I have an observed y value. Okay. Now, let's say that I want to estimate what my y value is going to be for each one of my x values. Okay. Now, we're already looking at the line of best fit, but let's say I didn't want to do a line of best fit. I just wanted a quick way of predicting what my y value was going to be. Okay. What I could use, and what we used before we started chapter 5, what we used as an estimate for our data was actually the mean. So what I could say is, regardless of the x value, let's say that an estimate for our y value, a prediction for each of my y values, is actually just going to be the mean of my y values. Okay. In this case, your mean is probably going to be around, I'd say, here. Okay. And the mean, we're going to denote by y bar, exactly as we did when we had just one list of data values. And we called each of those data points x, and we denoted their mean by x bar. In this case, we're going to denote the mean by y bar. Okay. What I'm doing is saying, regardless of the x value that I have, I'm going to say that my prediction for my y value for any given x value is just the mean of the y values. Okay. Pretty good prediction. Okay. We've used means before. But you can see that some of these data points have a huge error. Okay. And some of them have a tiny error. So you've got a pretty big variance in your errors here, okay? The difference between this error and this error is massive, okay? We know we can do better than that. What we have here, okay, is actually something that I'm going to call the total sum of squares, okay? The total sum of squares, and I'm going to do this on this page here. Okay, you're going to come across a few different terms here. But the total sum of squares is just going to be denoted by SST. I guess it's like sum of squares and their total. So it's actually denoted by SST. And it is this value here. Okay, so what I am doing here is I'm saying, okay, I'm taking each of my observed y values and I'm subtracting the mean and I am squaring that. And I'm doing that for every single one of my y values. And then I am adding them together. So let's come back to here. So what I am doing here is I'm taking a given y value. So let's say we're looking again at this data point here. I find its y value, which is somewhere up here, and I'm subtracting the mean from it. So I'm doing y minus y bar. So when I do that, I should get this error, y minus y bar. Okay. And then I'm squaring that. And then I'm adding all of those together for every single one of my data points. So then I go ahead and find another data point. Let's say this one here. I find its y value, which is somewhere over here. I subtract the mean, and then I square that value. So when I do y minus y bar, I should get this distance here. And then I square that. And I'm going to add those up for every single one of my y values. Okay. You should notice that if you actually take this here, this SST, if I divide that by n minus 1, you would actually find the sample variance of the y's. Okay. So that is called the total sum of squares. We've already seen the sum of squared errors. Okay. And all that was, let me come back to here, the sum of squared errors. Okay. That was when I had taken my line of best fit, it was the difference between my observed y value and my predicted y value using the line of best fit, and squaring that and then adding all of those together for every single one of my data points. So the sum of squared errors, and this was when I used my line of best fit. Okay, sum of squared errors was the sum of the errors squared, okay, which was just the sum of each of my observed y values minus my predicted y value for that given x value. And I square that for every single data point y, so every single one of my observations and every single one of my predicted values. I square that and I add them together. So what I have done this time is I've said, okay, well, my mean isn't a great way of finding some kind of prediction for my y values, okay? It's a pretty bad prediction because I can see I've got a very big variance in my errors here. So what I'm going to do is I'm going to try and move this line in such a way that I can minimize some of that variation in the errors. So I'm going to move this line up that way and down this way until I get a pretty good prediction for my line of best fit. So all you're going to do is rotate this line in such a way that it should go roughly through the middle of the data points, and I am minimizing the sum of the squares of the errors. Remember, for a line of best fit, that is your goal. You're trying to minimize this value. Okay? At the moment, the difference between each of the y values and your prediction for the y value using the mean, the sum of the squared of the errors isn't minimized. Okay, you have a huge difference between some of your errors, and some of your errors are huge. Okay, so you have a big variation in your errors here. You haven't minimized the sum of the squares of the errors. So by rotating your line of best fit, or rotating your mean line to create a line of best fit, you're trying to rotate it until the point that you have minimized the sum of the squares of the errors. Okay, so all you do is rotate that line until you have less of a variation in your errors, which means that the sum of the squares of the errors will be minimized. Okay, but you have corrected some of these errors. Okay, you now have, let's go back to our data point that's up here. Okay, that data point that was there. That error between the y value that we have, our observed y value, and our predicted y value, which is now roughly here, is much smaller. That error is now much smaller than it was. Okay? And that occurs for most of our data points. Okay, you've got some data points towards the middle where it hasn't made much of a difference. But you now have some data points where you have minimized that error. Okay, so you still have somewhat of an error with each of your data points, but it's not as much as it was. Okay, so if this was your total error to start with, your difference between y and the mean, and we square those to make them positive, this was like the error that you started with. This is the error that you end up with when we've gone from using our mean as our estimate to using our line of best fit as an estimate. We still have somewhat of an error left, being the sum of the squares of the errors, but we don't have as much of an error as we started with when we used our mean as our predictor. Okay, so there's still somewhat of an error, but it's nowhere near as much as we started with. So by using that line of best fit, we have corrected a lot of the errors. Okay, so when we started out, we used our mean as our predictor. We had these huge errors, okay, as we saw this difference here. Okay, we had some really big errors, as we do with like this data point here. Okay, we've got some really big errors when we look at using our mean as our predictor. But what I've done is I've spun that line in such a way and rotated it in such a way that I've minimized some of those errors. So now my difference between my predicted y value and my observed y value is now much smaller for most of my data points. Okay, you can see most of those data points are much closer to that green line than they are to the yellow line. So by using the line of best fit, I have minimized a lot of those errors. I haven't gotten rid of the errors entirely, but I've minimized and I've gotten rid of a lot of that error that we had. Okay, by using my line of best fit as a predictor instead of using my mean as a predictor. Okay. Because of that, we tend to call the sum of the squares of the errors. Remember, this is the sum of the squares of the errors that we are still left with. Even though we have used a line of best fit as our predictor, we still have these errors E for each of our data points. Okay, so this is the squares of the errors that we are left with, even when we use a line of best fit. So what we actually tend to call this is the total unexplained variation in Y. Okay, it's the total errors, well, the squares of the errors and summing them together. It's those errors that we are still left with, like we had here, and we've got an error here, and we've got an error here. Okay, it's the errors that we are still left with, even though we have used our line of best fit as a predictor instead of the mean. Okay, so it's the variation that cannot be explained by using a line of best fit. It's the variation that cannot be fixed. It's the errors that can't be fixed by using a line of best fit, okay? Those errors are still there, even though you've used a line of best fit. So it's the unexplained errors that are still left there. They're unexplained by the line of best fit. They're still there. But we have gotten rid of a lot of that error. Okay, so let's come back to our diagram here. Okay, let's look back at this data point down here. Okay, we started out with this huge error here, and we've reduced it just to that red line error there. Okay, so the difference between the two of those, I'll do it in grey actually, the difference between the two is this distance here. Okay, so it's the distance between the yellow line and the green line. Okay, that's the error that we were able to get rid of by using our line of best fit instead of our mean as a predictor. Okay, we got rid of all of this error here and are just left with this error that's here. So that is the error that is explained by the line of best fit. It's the error that was actually fixed by using our line of best fit instead of using our mean. Okay, it's the error that we got rid of. That is actually called the sum of the squares of regression. Okay, it's going to be denoted by, I've got to use a new page here, sum of the squares of regression. Okay, all that is it's the total sum of squares minus the sum of the squares of the errors, and it's denoted by SSR. So what is that? Come back to our, let's actually go to our formula, okay? Total sum of squares. All that was it's all the errors that we started with, the difference between each of our y values and the mean. We square those to make them positive and add them all together. So it's just the sum of the squares of all of these differences here. Okay, and I do that for every single data point. Okay, I square each of those differences between the observed y value and my mean. And I square those and add them together. Okay, so it's the sum of the squares of the errors that I start with. Okay, then what I did was I spun that line around and I said, okay, now I'm going to use my line of best fit as a predictor. But I'm still left with some of those errors. Okay, so the sum of the squares of the errors was that SSE value. It's the sum of the squares of the errors that I am still left with when I have gone ahead and used that line of best fit. So it's the sum of the squares of these distances here. Okay, it's the sum of the squares of the errors that I am still left with even though I've used the line of best fit. Okay, so if I do the total errors that I started with squared and add them together, and I subtract the errors squared that I am still left with when I have used the line of best fit, I should end up with the sum of the squares of regression, which is a measurement of what I have fixed, okay, by using my line of best fit instead of using that mean. Okay, so it's the amount, again, going to be positive, that I have managed to fix by using the line of best fit instead of using my mean. So it's just a measurement of basically the difference, like I have with each of these grey lines here. It's the amount of it that I have fixed by using a line of best fit instead of my mean. And that is called the sum of the squares of regression. It's the amount of the errors that I have fixed by using the line of best fit instead of using something else, in this case the mean, as a predictor for each of my y values for any given x. Okay, so that is called the sum of the squares of regression. So it's the total errors squared that I started with, all added together, minus the errors that I'm left with squared added together by using my line of best fit instead of using the mean in my total sum of squares. Okay. So we can see this kind of makes sense. Okay. The total error that I started with, again, it's all squared to make sure it's positive, but the total error that I started with by using my mean is equal to the total error that is fixed by using my line of best fit, the amount of errors that I could get rid of by using my line of best fit instead, plus the errors that I am still left with from using my line of best fit. So this is the amount that was fixed by using my line of best fit, the amount of errors that I could get rid of by using the line of best fit instead of the mean. And this is the errors that I'm still left with even though I have used my line of best fit. Okay? And that should equal the total error. Okay? It's the amount that I could fix plus the amount that I couldn't fix should equal the total error. Okay. All of this to say, and as I said, it is very algebraic and it may take a couple of times of looking at this to kind of figure it out. All of this to say, there is now another term that we will use, and it is called the coefficient of determination. And the coefficient of determination tells me what proportion of my errors can be corrected by using the line of best fit. Okay, so remember, this is the amount of the error that could be corrected by using the line of best fit, and this was my total error. So the proportion of the errors that could be corrected by using the line of best fit should be the amount that was corrected divided by the total errors. Okay, so the coefficient of determination is the proportion of the errors that could be gotten rid of or fixed or corrected Okay, so it's the proportion of those errors that are made up by those that I can get rid of by using my line of best fit instead of my mean. So all that is SSR divided by SST. So it's the amount that could be corrected by using the line of best fit, the amount that I got rid of by using the line of best fit, divided by the total errors that I had to start with. Okay, so it's the amount that was corrected divided by the total errors. This actually has a name, coefficient of determination. It has a particular way of denoting it, which should look kind of familiar. And that is R squared. Okay. Remember, your correlation coefficient was denoted by R. And that was a value that was between -1 and 1. Closer it was to 0, it said that your data had less correlation. Closer it was to 1 or -1 meant it had a stronger correlation. Closer to 1, it had positive correlation. Closer to -1, it had negative correlation. But the more perfectly it was in a straight line, if it was close to 1 or -1. Coefficient of determination is actually R squared. This is where that R value comes from. Okay. What you have here is a fraction. Okay. If SST is the total error and SSR is the amount of error that was corrected by using the line of best fit, SSR is always less than SST. okay, you have a fraction here that is less than 1, okay, or is at most 1. So r squared is always between 0 and 1, okay, because you can't correct more than what you started with, okay. SST is the total error. I can't correct more than that total error, okay. So r squared is always between 0 and 1. If I were to square root this, okay, if I square root 0, I get 0. If I square root 1, I can have 1 or negative 1. That is why your r value is between 1 and negative 1. So the correlation coefficient is just the square root of this. And that's where the correlation coefficient comes from. Okay. There's several different ways that you can figure out r squared, okay? SSR divided by SST. SSR, if we come back here, this is just as a side note in case you ever come across this. If it's SST is equal to SSR plus SSE, okay, that means SSR is equal to SST minus SSE. So if I go ahead and write that, okay, fraction theory, okay, if I've got two things subtracted from one another divided by some number, okay, I can rewrite that as SST over SST minus SSE over SST. This thing here is just 1 minus SSE over SST. Okay, so a couple of different ways of writing this, but all you need to know is it's the proportion of the errors that are corrected by using the line of best fit. Let's see what happens when r squared is at the two ends, when it's either 0 or 1. Okay, when r squared is 0, okay, that must mean that the numerator of the fraction is 0, because 0 divided by anything is still 0. So when r squared is 0, that must mean that SSR is equal to 0. Okay? So that tells me that my line of best fit didn't correct anything. Okay? I am still left with all of the errors that I started with. So my total errors that I am left with must equal to the total number of errors that I started with. So when r squared is equal to 0, which would mean that r is equal to 0, it means that my data is so scattered and so all over the place that a line of best fit doesn't help me in any way whatsoever. Okay, so whether I use my mean or I use my line of best fit, nothing's been corrected. Okay, I'm still left with all the same errors that I started with. That must mean that my data is so scattered and all over the place with no correlation whatsoever that the line of best fit just doesn't help. So all the errors that I start with equal the total errors, okay? Because all the errors that I start with, okay, will equal the errors that I'm left with at the end by using a line of best fit, because my data is just so scattered and all over the place and would probably look something like this. Okay, so whether I use my mean or I use my line of best fit, I still have all these massive errors and my line of best fit hasn't helped whatsoever. Okay, so when r squared is 0, that means that r must be 0, which means I've got no correlation, so my line of best fit doesn't help whatsoever. When r squared is equal to 1, okay, going back to our formula, when r squared is equal to 1, that must mean that these two things, SSR and SST, must be equal. Because then I would have, if SSR equals SST, then I would have SST divided by SST, which just gives me 1. So when R squared is equal to 1, those two things must be equal. Okay? So that tells me that the total errors that I started with equal all of the errors that I corrected by using my line of best fit. That means I corrected every single one of my errors. Okay, so let's think about this. You can see why this would be. Okay, this is my data set. I originally used my mean of the y values as my predictor. But now I'm using my line of best fit. My line of best fit hits all of the data points. That means the errors have gone down to 0, which means that my line of best fit corrected every single one of those errors. So my total errors have now gone down to 0. So SSR, the errors that were corrected by my line of best fit, equal the total errors that I started with because I've corrected every single one of those errors. So it means that the model corrects all of that variation in the errors. It corrects every single one of my errors. So my points must lie on a dead straight line. So when R squared is equal to 1, we know that R is equal to -1 or R is equal to 1, which must mean that my data points lie on a direct straight line. Okay, so that's how this stuff kind of all goes together and how it links to our correlation coefficient, okay, in terms of our errors. So let's, as a last thing before I talk about Excel, the closer that R squared is to 1, okay, as we had here, the closer that R squared is to 1, the more that the line of best fit helps to lessen the variation in the y value. So the closer that R squared is to 1, the more that that line of best fit corrected all of those errors, the less of a variation that you will have in those errors. Okay, so if R squared, let's say, equals 0.91, we're pretty close to 1 here, okay? We know that our R value is going to be pretty high. We're going to have some decent correlation happening here. So if R squared was equal to 0.91, that actually means, in terms of words, that your line of best fit corrected 91% of the variation in the errors. Okay, because remember, R squared is a proportion. Okay, that meant that if R squared is 0.91, okay, remember R squared is a proportion, so you could put it as 91%, okay? Your line of best fit in this case would have corrected 91% of those errors. It's corrected 91% of the variation in the errors, okay, because you had a lot of variation to start out with, okay, and now by using the line of best fit, you have corrected 91% of that, okay, of the errors that you started with, which is great, okay. Whenever you have an R squared value that is pretty close to 1, that is great because it means that you've got great correlation and that line of best fit fixes a lot of what you started with. So you always like to try for an R squared value that is pretty high. Again, going back to Excel, because you're going to have to be able to read these values off. If you are looking for, so I'll write this all down. In Excel, if you are looking for SSR for a particular data set, so the amount of the errors that were corrected by using your line of best fit, that is done under regression, SS. Okay, you will be running these programs, but Hawks will have a picture of the actual Excel so that you can pick the values off for any particular data set, but you will actually do it for your own data set in the next application. But Hawks expects you to be able to read the Excel document off. So if you're looking for the sum of the squares of regression, it's under regression SS. If you are looking for SSE, it's under residual SS. And if you are looking for SST, it's called total SS. Okay, so remember back at the start, we had our variance of the errors and our standard deviation of the errors. The variance of the errors was found under, so variance of errors, okay, that was found under residual MS. If you wanted the standard deviation of the errors, that was found under standard error in the Excel program that you run. And then we've got SSR, SSE, and SST can be found under regression SS, residual SS, and total SS. Okay, so whenever you have a data set, okay, you've got the X values and the Y values. Okay, to sum up what we've done here, we've started out with, we've got these observed X and Y values. Okay, let's say that for some other particular X value, I want to estimate what its Y value would be. Well, a good place to start, as we looked at the start of the course, good place to start out if you ever need a prediction for something is the mean. So I'm going to predict that for a certain X value that I don't yet have the information for, I'm going to predict for that X value that my Y value would be the mean of the Y values that I already have. Okay? Good start, but we can do better than that. So instead of using my mean, what I'm going to do is I'm going to move that line and I'm going to rotate it to be my line of best fit that goes through the middle of my data points. Now I'm going to estimate that my predicted Y value for a particular X value is going to be the Y value that I can pick off of that line of best fit when I plug in that particular X value. Okay, now that line of best fit is much better because what I have done is I've gotten rid of a lot of the errors that I started out with, the errors being the difference between each of my observed Y values and my mean, okay, was actually quite large. I had quite a lot of variation in my errors. I had some very large errors and some very small errors, which meant that it wasn't a great predictor. So to make that predictor better, I made my line of best fit. Those errors now had less of a variation. Okay, most of the errors were around the same size. So that was great. So it made a much better predictor for any given X value. I could find a better prediction for my Y values. Okay, and that is why we like it. As I said, this is incredibly algebraic and it's not exactly the easiest thing to understand, particularly when you start out. On both Monday and Tuesday of this week, I would be more than happy to go through this again in class and draw some of this out if anyone is getting stuck. I know that this is quite a difficult thing to visualize and understand what is going on. It's very, very theoretical and not exactly the most intuitive thing to understand. So please come to class on Monday and Tuesday if you have any questions about this, and I would be more than happy to help you. The Hawks homework for this will expect you to know how to pick these values off of an Excel document. It will have like a screenshot of what it looks like in Excel, and we will be doing that in the applications. But make sure that you know what each of these values means. So if you need to take a screenshot of this just to help you like pinpoint which value is which, that would be great. But as I said, if you've got any questions about this, please come to class on Monday or Tuesday and I'd be more than happy to help you because I know this isn't easy. Let me know if you have any questions, text, call or email me and I'd be more than happy to help, and I will see you in the next video.